All right, thanks, Addy. Thanks, everybody. And it's interesting hearing about NETRO, and which is pretty close to Petro, so we'll take that as a nice connection. I wanted to take some time here today to talk a little bit about the lunar science perspective. Ryan will be coming after me to talk about PSI and PSD. I promise I won't use too many more acronyms. That said, I also want to focus on a little bit of what LRO has done and can contribute in the future in constraining the effects of Plume-Surface interactions on the surface. Let's go to our next slide, please. So we're at a really interesting point in lunar exploration. We are about to kind of dive into sort of an unprecedented history of exploration. We've seen the first tentative steps of that with commercial attempts at landing, with Intuitive Machines' successful landing, and you know the interesting experience that they had on the moon, and of course we look forward to several more opportunities on the lunar surface to come. It's a great time to start thinking about what it is we are going to be doing to the surface as we explore. At one point, I want to make sure everybody takes away from today and tomorrow is that I hope that we view PSI as not a threat, but as a part of exploration, as a science opportunity. We're going to be going back to the lunar surface, and we're going to be changing that environment. To which scale, to which degree, and how much of a change across which spatial scales. In all of that lies opportunity for science, understanding the environment of the moon as it is right now and how it changes with exploration. Over the last 15 years, we've had one of the most remarkable assets in orbit around the moon in the form of LRO. I'll talk a little bit about what LRO has done and can do in the future to constrain the effects of PSI on the surface. But of course, I also want to leave everyone the notion that LRO is an asset that we count on, we put a lot of weight into, but may not be around forever. We've done heroic things to keep LRO alive now for over 15 years. But every morning I wake up, we all wake up with the expectation that Mother Nature is in control of the spacecraft, and Mother Nature is a fickle entity. So what more can LRO do? But then what can be done with subsequent orbiters as well are some of the topics I'd like to talk about. One of the guidance, let's go to the next slide, that we were presented with for the presentations, I wanted to seed the audience with a question. How can diverse orbital measurements constrain plume surface interactions? Again, I think LRO has done a tremendous job of doing that over its 15 years. But if we were to identify a future orbital mission that could really help constrain this problem, what are the types of instruments, the types of measurements that we'd want to make from orbit? Of course, at right is an image from the Apollo 15 mission, the panic chromatic imaging system that was on orbit with Apollo 15. And you can see in the middle right, a small smudge around the lander, right? So we've been characterizing plume surface interactions from orbit for over 50 years. I'd remind everyone, of course, that when you read the Apollo 15 preliminary science report, there's no great degradation of science that was done. Certainly, the effects to the area immediately around the lunar module were known and recognized, characterized in exquisite detail through measurements on Apollos 11 through 14 with the stereo close-up camera. But the science results of Apollo continue to be rich despite the effects of plume surface interaction, including the hardware that was left behind, the mirrors of which on Apollos 11, 14, and 15 continue to reflect photons back to the Earth today. So, as much as PSI is something we need to be attuned to, I hope that our science colleagues are not running in fear from it, rather running towards it as an opportunity to learn more about this unique environment that we are going to be exploring. Next slide, please. So let's talk about LRO, the past and the present. LRO was supposed to be in orbit from anywhere from 1 to 3 years, starting in June of 2009. Here we are now 15 years later, a little heavier, a little less hair, but still running this incredible mission that is dramatically changed our perspective of the moon over that time. We initially were in a 50 by 50 kilometer polar orbit, and everyone's very familiar with the high resolution images that we've returned from that time. In late 2011, we were placed into an elliptical orbit, similar to what we had in our early commissioning orbit. And basically in doing so, took our foot off the accelerator and allowed us to enter a fuel savings orbit, an orbit that we continue to leverage to this day. In doing so, we've now created this incredible database of observations, and there's an example of which I have at the bottom right. One of my honestly favorite set of observations of all time. Sometimes it's better to be lucky than it is to be smart, credo that I have lived up to this day. What is shown there are the images of the Chang'e 5 landing site. The image at left is the lander immediately or shortly after landing, but before the ascent vehicle departed the surface. The image at right is after the ascent vehicle. So we have here this wonderful experiment of the before, the after landing, before ascent, and the after ascent of the return capsule. And so the LRO data set is obviously open for use. We encourage everyone to go and interrogate it. And as we land more missions to the surface, as we do more lunar exploration, the results, not just from the camera system, but from other instruments, should definitely be integrated into our understanding of PSI as well as our modeling efforts. Let's go to our next slide, please. But that's to say, of course, we have a rich cadre of other measurements that have been made in lunar orbit while LRO has been there. We should not forget the LADEE mission. Of course, LADEE had a number of instruments on board, including a mass spectrometer, and that mass spectrometer measured the effects of the descent of Chang'e 3 to the surface. And of course, in doing so, was able to characterize the diffusion of its fuel around the lunar surface, around the moon, over several orbits. And so, here's an interesting additional piece of data. Does it have the same fidelity, same spatial resolution as our orbital images? Certainly not, but it's an additional data set. And so what I hope to at least convey to you here is that orbital measurements, as well as measurements made on landers, as well as measurements made on the surface, are a valuable and important part of telling the whole story of how we're changing the surface and ultimately the global exosphere around the moon. I know Parvati would hopefully echo some of these sentiments that there's much that we can do from lunar orbit, that we should not ignore the opportunities that orbital assets pay in understanding the changes to the surface. Let's go to our next slide, please. So right now, LRO is proposing for a 6th extended mission. With each extended mission, we learn more about the surface of the moon and how it changes over time. We have a strong commitment to supporting missions to the surface, whether it's an Artemis mission, a PRISM missions, CLIPS missions. We want to ensure that this new era of lunar exploration is done so with the best possible orbital data. I'll remind everyone that we fly over any particular target on the surface of the moon about 1 time a month. We'll fly over a spot on the surface that's in darkness and in light, basically twice a month. In addition to the high resolution images that we all know and love, and again, examples of the blast zones around Apollo, Luna, and Surveyor sites is at bottom. You'll see more of this image in Ryan's talk. We have other instruments on LRO. We should not be surprised that the LAMP instrument has been used in the past to constrain changes to the exosphere. It's a very challenging measurement to make for landed missions, but every time there's a landed mission to the moon, LAMP certainly looks at the opportunity to characterize changes to the exosphere. We have the Diviner instrument, which measures the thermal properties of the surface. Now, again, at large spatial scales, but as some of our modeling colleagues, will say, perhaps some of these changes we might see over to the surface may exist over large spatial scales. And of course, Diviner also probes the subsurface. So we expect that a large change to the surface would be reflected in the Diviner data. Again, we can constrain that. And of course, Mini-RF for near-side targets can constrain bulk changes of regolith over hundreds of square meters to meters of depth. So depending on the spatial scale and the depth scale of change, LRO can help constrain that. But as with everything in planetary science, there's a but. There's a pretty big but here. Let's go to our next slide. Of course, with time and this rich history of operating at the moon, there comes a cost. Now, this is a feature, not a bug, in the system. When we got to the moon, of course, we were orbiting perfectly over the poles. With time, our inclination has drifted away from the poles. The bottom right figure, now my advisor, Carly Peters, loves to show spectra. The best I can do in this talk is not a squiggly line of spectra, but a squiggly line of our inclination, going from directly passing over the poles to an inclination of roughly about 5 degrees now. That means that there are portions of the polar environment that we do not pass directly over. This does mean, however, that there are parts of the poles that we pass over regularly over every orbit, a density of coverage now that extends away from the poles. So over the 15 years, we have this incredible density of observations of the polar environment. But today, if we had to image an area near the pole, we have to rely on SLUs. As an example of a SLU Dalrock NAC image at lower left. And in doing so, it changes the spatial scale and, of course, what we can discern for any particular image. That is, however, to say that the rest of the moon away from the poles, from about 85 degrees South Pole to North Pole, we have excellent coverage opportunity for. And so for missions that are planning to go to effectively anywhere on the moon, LRO observations can help constrain the changes to the surface and the changes to the environment that we encounter. Let's go to our next slide, please. So again, I want to remind and emphasize the point that I think PSI is an opportunity. There's an opportunity for science. Not every science activity that we want to encounter on Artemis 3, for instance, is going to be negatively impacted, pardon the pun, by PSI. That there are a number of investigations that we're currently exploring for Artemis 3 that will not be negated by the effects of Plume-Surface interactions. And of course, over extended stays on the lunar surface, the buildup of infrastructure, we need to account for the effects of Plume-Surface interactions on deployed hardware. But again, there's an opportunity for understanding the environment that we are going to be working in over the next several decades and hopefully centuries to come. I would encourage everyone not to ignore the opportunity and the importance of orbital observations to constrain these effects on both the local, the hyperlocal scale, regional, and a global scale. And so what I would encourage this community to help us with is identify what are those observations that should, could, and need to be made in order to best constrain the effects of landing and ascent on the entire surface of the moon. And as a reminder, we are in the process of proposing for a 3-year extension. Will take us to 2028. And after that, we have the opportunity to propose an additional 3-year investigation. Again, I want to emphasize the point that LRO is an asset that we should be counting on, but that we cannot solely rely on for long-term, decades to come observations. And so now is the time to start planning for those subsequent orbital observations. And so I ask this community to help us identify what those observations should be. The last thing I'll leave is the question of opportunity. There are hundreds of parts of Surveyor 3 that reside in the curation facilities. There's a recent, I guess now recent is 2011, but there was the most recent look at Surveyor hardware through Immer et al., and we'll hear more from Phil Metzger shortly. And I'd say it's high time that there be a deeper study of the parts that were returned from Surveyor 3 by a larger community. We've seen the benefit of things like consortia studies through the ANXA program. Well, I think now is the time for ANXA Prime on looking at Surveyor hardware that were returned and putting that into context with the orbital observations that we have from LRO to understand exactly what happened those many years ago. I will now save time for questions, and thank you for your time and attention today. Appreciate it.
Thanks, Noah.
Let's see. I don't reminder that y'all can put questions in the IO tool link. I have a quick question. So you've mentioned a lot about sort of the science opportunities or the let's say mission, how you can use science data for missions. I guess I would maybe turn the question around and go for people developing instruments, let's say to observe PSI for mission focus needs. What opportunities for science do you see in those, if any, or what would you, is there?
I would say, certainly anything from regolith dynamic. There's all of the PSI effects of understanding the regolith. When we start taking these controlled experiments, landings to multiple places, we can gain insight into regolith property differences. This is the difficulty, the glorious difficulty of the moon is how both ubiquitous, uniform, and non-uniform surface features can be. And so as we start landing, if we have a consistent set of measurements done mission to mission, or we're not comparing apples and oranges or apples and bananas, but we're saying similar measurements done consistently on mission to mission to mission scale, the same way we have certain uniformity in data expectations for data archiving. Well, let's collect the same kind of data on every single mission and buy down that uncertainty in local properties through uniform measurements. If we have one set of measurements on landing 1 and a completely different yet comparable set of measurements on mission 2, how do we unify? How do we connect those two disparate sets of observations? I think we have to simplify the problem for ourselves and not, burden future graduate students to try to clean up the, uncertainty in measurement to measurements and different types of measurements, and try to really approach this as a tractable problem through kind of, I don't know, being uniform about it. And now as I eat into Ryan's time, I will just say that I think we can do that. We just have to be smart about it. And I know that everyone will take a moment of snark and saying, well, that's not the NASA way. That has to be the NASA way to do it. Thank you for laughing. But I think we just have to go in and say, let's make this a tractable problem, because it is tractable if we allow it to do so.